So thank you for coming to the presentation today. I'm really excited to be here in this beautiful venue to talk a little bit about the project that I've been working on for the past several months, as well as TensorFlow in general, if you have any questions about the framework. So to get a little bit of a feel for the room, how many of you are Python developers? Couple? Cool. How many of you are machine learning engineers? Couple more hands. All right, and then how many of you are just interested in deep learning because maybe you saw some salaries posted somewhere and it looked pretty interesting? Cool. So hopefully there's something of use to you in this talk. Swift for TensorFlow is a little bit different than TensorFlow in general. It's kind of a reimagining of the project itself. I hope that there will be some good questions towards the end. So a little bit of background. My name is Paige Bailey. I'm currently a product manager on the TensorFlow team at Google Brain, working both on TensorFlow's APIs, particularly its core APIs, as well as Swift. I've had a little bit over a decade of experience doing machine learning at places like NASA and Chevron, and just before Google at Microsoft. And my background is not computer science at all, other than some master's work. It's geophysics and applied math. So coming at it from a bit of that perspective. I also did not have any experience working with Swift prior to starting on this project. So it's been a little bit of a roller coaster ride. How many of you have used Swift before or have seen it? Okay, so a few more hands than Python. So hopefully this will be fun. So an outline for today. What is Swift for TensorFlow and why is it different? Why is it particularly useful for deep learning? And then also some ideas of how you can get started if you would like to. So deep learning has really taken over in the past several years, right? It's gone from being sort of a research project to being something that's ingrained in every single application that you use in your life, right? So you're able to take models, easily port them to browsers, to mobile devices, to do things like computer vision tasks, but also really interesting things like natural language processing, to do automatic text generation, to be able to do speech recognition or speech transcription. And this is all happening in near real time on your devices. So this is great. It's wonderful that sort of machine learning and deep learning have become so ubiquitous. But it also means that you have a lot of constraints that weren't necessarily apparent when this field first started for your deployment targets. So being able to port something like BERT to a mobile device, that is not a light challenge, right? Like these models are megabytes in size, even just kind of the weights of the graphs themselves, and finding ways to quantize them efficiently and make them performant is really, really trying. We've also seen an explosion of interest in the research space, right? So not just these production and very lucrative businessy sorts of deployments, but also the number of archive papers per year. So here you can see that we've actually surpassed Moore's law as of 2017. And if I had extended this chart to 2019, it would be even more impressive, right? Like we're hitting these exponential growth curves that are sort of delightful to see, but also a little bit staggering because some of the papers that are produced are not necessarily immediately applicable to us in our everyday lives, but many of them are models that are highly interesting and could offer substantial business value if you were able to incorporate them into your web app. And so what we see are people who want to be able to convert these models as quickly as possible and get them into production. We've also seen rapid accuracy improvements. These are some examples of image recognition and sort of object detection models, and you can see these step change performance improvements over time, but it's becoming harder and harder to get these without doing sort of interesting algorithmic fusion techniques. So being able to take sort of traditional methods like Monte Carlo tree search and marry it with some of these deep learning techniques. And of course, deep learning is central to everything that we do at Google and Alphabet. So you can see here on the left the number of unique project directories with deep learning models at Alphabet over time. The trend continues through 2019, and we've started incorporating models into every single one of our products. So everything from YouTube to Drive to Android. So for example, if you have a Pixel device, you might have noticed that just recently speech to text, if you speak into your phone, got very, very speedy. And that is largely due to TensorFlow Lite models being embedded directly on your mobile device. So instead of having to speak into your phone and then go and ping a server somewhere with the data and then come back, now that is done directly on your cell phone. So your data has stayed secure, and also you have much lower latency. We've also seen an explosion of specialized hardware. Right, so here you can see some examples of TPUs over time. Our first generation TPU was just for inference, so just to be able to get results from machine learning, not from training. And then we've continuously built out the scale and the capabilities of these pods. So at the bottom, you can see the latest version of our TPUs that are currently available on Google Cloud and in Google data centers. These allow scientists to be able to run models that historically would have taken weeks in just a matter of minutes or hours. And if that's the case, you suddenly get into this state where instead of having, a delay in your experimentation process, you're able to truly do rapid prototyping. And if you get results immediately, if you're able to set off an experiment and then go and get a coffee and find out if what you decided was right or wrong, you can really start innovating much more effectively. So all of this is great, right? Like why Swift? Why is it useful, particularly for these scenarios that I just described? So these more novel, these sort of novel deployment targets, specialized hardware, this need and desire to be able to do things like algorithmic fusion. And for this, one of the examples I always like to give is from a book called Python Interviews. And it details a story from when Google was first starting out. It was trying to match the speed and the productivity of one of the startups that was operating in the Bay Area. And they were so shocked that this startup, this tiny team was able to iterate so quickly, that they had, and maybe they and Google had the same idea at the same time, but this startup was able to ship features very rapidly. And Google, who was using C++ at the time, was cranking out features much more slowly. And then after they acquired the company, now called YouTube, they realized that the reason why they were able to crank out these enhancements so quickly was because they were using Python as opposed to C++. And even if the first bit of performance wasn't necessarily as great as you would get from C++, you could fine-tune it as soon as you had a minimum viable product, right? Like you get the first thing that works out the door, and then you can start doing these performance enhancements. And the cool thing is that for those things that I mentioned, most of the development work is done in languages like C++, right? Like it is what people, that is sort of the norm for people who want to deploy things to embedded devices, maybe C instead. If you want to deploy models to mobile devices, if you want to be able to do these very sort of bespoke configurations for distributed training, you're probably doing them in C++. And C++ is painful often. It's great in the sense that Python is also painful for different reasons, but C++ takes a great deal of time. It's often difficult to understand for people who don't come from that particular background, and it doesn't give you the affordance of being able to rapidly prototype. Swift gives you all of the performance benefits of C++. So we continuously see performance just as quick as C++ or C even. But it gives you a syntax that's very friendly and feels very similar to Python. So I'm not sure how many of you have seen Swift code before. That's an example on the screen. You know, it might have some lets sprinkled in and a few more curly braces maybe, or some indications of types. But if you squint a little bit, it looks a lot like Python, right? And so if you have a situation where you're able to do these very sort of low-level tasks in a language that looks like Python, the world is suddenly a bit brighter, right? And so here you would see an example of an image classification model using Swift for TensorFlow. You have a model, you have some layers that you define up top, and then in order to actually differentiate through those layers, all you would have to do is sort of decorate your function with @differentiable. And this is capability that we're upstreaming to the Swift programming language itself. So any function, literally anything, not even if it's machine learning related, you would be able to differentiate through it to get the gradients, to get the change over time with just this short prefix. We're integrating differentiation and these things that have traditionally been thought of as very machine learning specific directly into the language because we believe them to be that important. If you want to train your model, all you would have to do is define some optimizers, maybe some distributions, and then set a for loop and you're off to the races, right? So it looks just as you would imagine. It's very straightforward, syntax almost identical to how it would be in Python, but you're still getting the performance benefits that you would have using a language like C++. And this is just another example taken from a recent course that was taught by Jeremy Howard, who is the creator of fast.ai. You can see an implementation of a model in Swift up top, and then the same model implemented in Python down at the bottom. It's actually kind of funny in that the Swift model is a little bit more concise than the Python version. But they look, again, pretty similar. And pretty straightforward to understand. Another nice thing. So how many of you have looked at assembly recently? Not very many hands. But if you did want to go take a look at Godbolt, I strongly suggest it. It's a lot of fun to see kind of how the different languages that you use every day sort of translate themselves to assembly code. And what you see on the left is a function implemented in Swift, and on the right, the equivalent assembly code. And that's about as sort of efficient as you can get, right? Like every single thing that you see happening on the left is sort of directly correlated with what you see on the right. If you tried to do the same thing with Python, you would probably be a little bit surprised. Yes, so godbolt.org, lots of fun to play with. The next bit that I would talk about, specifically how Swift is afforded to mathematical operations, scientific computing, and machine learning in general, is value semantics. So with Python, you have sort of the concept of value semantics for integers, right? Or for variable assignments, rather. So quick question. If you print B on this screen, what is the output? Just shout it out. Yep, I heard it in the audience. So it's 3, right? Because Python for this assignment follows something called value semantics. But if you have lists, right? So if you do the same sort of concept but with a list, what you're going to get is a little bit different. You're getting reference semantics. And that is not how math works, right? So Swift arrays follow value semantics for everything. So you have a similar situation, and with Swift, you get precisely what you would expect. And that's the sort of rationale for this why this would be beneficial is because that is how math works. And if you're able to have a language that operates in the same way as you would expect mathematically, life is a great deal easier, and variable handling especially is much better. Automatic differentiation in Swift. So I was having a little bit of trouble with the internet a little bit earlier. So I'm not going to go through the exercise of executing all of these cells in our example notebook. But we do have this available on github.com/TensorFlow/Swift if you would like to take a look and try it out yourself. How many of you have used Colab notebooks before, or Jupyter notebooks? All right, so several hands. If you haven't ever experienced them before, I strongly suggest taking a look. They are really fun ways to sort of understand models that you create, and then also to immediately get responses for the work that you're doing. And all of these cells that you see, they're either markdown or language cells that are immediately executable. So you can see here a little play button. You can also hit Shift-Enter, and each cell executes. This is all done for free. In Colab, using CPU, GPU, or TPU, you can actually toggle between the runtime types in the notebook as you work. But here you see an example of differentiable programming using Swift. You have a function, some gradients, and you can see here an example of doing that differentiation on a function, particularly square roots, and creating a custom derivative for square roots. And this is partially because everything in Swift, like even the types, are fully customizable. So if you want to have a custom type, example bfloat16, which is what you would need in order to run on TPUs, you're able to create that directly within the language. This is also an example of sort of the C interop, which we'll talk about a little bit later. You can import any header or library from C or C++ and use it exactly as you would expect. And again, we have a huge collection of demos available on GitHub. Strongly suggest taking a look and trying them out yourself. So Swift for machine learning. It is cross-platform, and this was something that surprised me when I first started with Swift. I had always had kind of the understanding that it was an Apple language, maybe. Like it worked on all of those things that were prefixed with I, like iPhones, iPads, maybe the things that were prefixed with Mac too. But it actually can go anywhere C++ can go. So that means Linux, Mac OS, Windows, Android, iOS, and even embedded devices. There have been a number of sort of theses and projects recently showing that you can get the binary size of Swift reduced down to something like 1.4 megs. And that means that you can start running it on really interesting deployments, targets. And syntactically, it's very similar to Kotlin. So if you were an Android developer and you wanted to be able to use Swift inside of your Android app, you could just compile your model down to a .so file and call it as you would any other library, right? So that's really, really sort of interesting to understand. It also means you can write your model once and deploy it anywhere. So instead of having to create a completely different pipeline for data ingestion, data preprocessing, model building, and then sort of the post-processing step for your model, for the, if you're operating on iPhone, or if you're operating on a server, or if you're operating on an Android device, you can just have a single pipeline for all of it and deploy. It also gives a lot of productivity and customizability, right? So with typed APIs, static detection of errors, you also have nice things like semantic-aware autocomplete and jump to definition. And you also have customizable abstractions in user space. And it's also being integrated, or in the process of being integrated as syntactic sugar for something called MLIR. So how many of you have heard of MLIR? Excellent. So MLIR is a new project from Chris Latner, who is also responsible for LLVM, the Swift programming language itself. Really great guy to work with, very sort of bright and focused on community. But MLIR is a new project that's specifically focused on taking the pain out of having complex deployments. So what does that mean? That means, so for example, right now, if I was implementing a model, and I was using something called like scikit-learn maybe, which currently only works on CPUs. If I wanted to deploy that to a server or to a phone for some reason, we would run into the constraint where maybe some of those ops would work on each target, and maybe they wouldn't, right? Or to be maybe a little bit more concrete, if I had developed a model using TensorFlow, maybe the Python version, some of those ops might be GPU accelerated. And if you deploy to a target that doesn't have sort of that afforded to it, there's no guarantee that that sort of bit of model building would be punted back to the CPU to run as opposed to attempting to run on GPUs. So you might have a silent fail, you might just get bad numeric responses, or just bad things would happen. Right? Like it's problematic in that you essentially have to hard code everything that you build to work on to the places that you want to deploy them to. And when you think about the mobile device space with thousands of different, hundreds of thousands of different kinds of devices, all of which have different kinds of hardware, very difficult to know like what your user is, like what to expect. Like, does your user have a mid-tier device, a low-tier device, a high-tier device? If you do deploy a model, like what is the confidence that you have that it will actually execute in the way that you expect it to? It's just very problematic, way too complex. And so MLIR is building on top of something called LLVM, and it allows you, provided there's an MLIR dialect, to write your model once and to deploy it anywhere. And not have to worry about the complexities of those targets. It's also an open source project that was recently open sourced to the LLVM Foundation, and they have open design meetings every Thursday at 10 a.m. So if you would like to learn more, strongly suggest sort of subscribing to the mailing list and staying informed. Swift is also interoperable. I think I mentioned this a bit earlier, but there are no wrappers. You can just import libraries directly from C and call it. So here you see importing glibc. We also have C++ interop. So this is something that an engineer on our team named Parker has been working really diligently on. You're able to pull in any arbitrary header and then use it directly or extend it in ways to meet your use case. And this is really exciting, particularly if you're operating in a company with a lot of C++, a lot of historic code that's very useful and lucrative to your business. An example would be Google. And you don't want to have to rewrite the world in order to use a new language. There's also interoperability with Python. So if you are coming from the Python space, you probably realize that there are a ton of data science libraries available that make life a great deal easier. So examples would be NumPy or SciPy or Matplotlib or Seaborn or any of the other data visualization or data preprocessing or sort of machine learning capabilities for traditional tasks. With Swift, you import Python and you use it just as you would in a Python IDE. All right, so you can import NumPy, use it in an array, and get back exactly the sort of values that you would expect. And this is all implemented in pure Swift. You can also create custom kernels directly in Swift with the Jupyter Notebook. So here you see an example of 1D average pooling. An engineer on our team named Eugene also has implemented a custom CUDA kernel inside of a Jupyter Notebook. And historically, those would have been sort of very difficult or impossible even to include in your machine learning models. And now they're just as simple as being able to implement a few lines. So with differentiable programming, you can also have custom derivatives, user-defined types, and it's flexible where you need it. We have language integrated autodiff, which I showed a little bit easier, or a little bit earlier. You prefix any function with that differentiable, and you're off to the races. And for performance, It's just as good as C++, often just as good as C. You can also have multiple threading, so you're not at the mercy of the GIL. Python is single-threaded, and you also can have graph extraction. This is a picture that was taken from a recent course that Jeremy Howard, the author of fast.ai, taught with Chris Latner. Both of them are available on YouTube if you'd like to learn more. They're about 3 hours long, but they're really exciting watches. And they kind of run through the concepts of machine learning implemented in Swift and in Python, and then also why something like Swift is incredibly useful for machine learning tasks. I also think that it's interesting. Jeremy sort of famously was a very avid TensorFlow user, and then migrated to PyTorch specifically for performance considerations. The things that he needed to do in TensorFlow just weren't as fast as the computations he was able to get in PyTorch, at least not at the time. And then after working with PyTorch for a bit, he transitioned back to TensorFlow, specifically for Swift for TensorFlow. So he's taken his fast.ai library, which is very popular and sort of a concise way of expressing machine learning concepts, and he's ported the entire thing to Swift. And he's calling it Swift AI instead of fast AI because puns are awesome. But it's also available on GitHub if anybody wants to try it out. We've also been working really closely with the AlphaZero team and the AlphaGo Zero team. And this is a kind of a perfect partnership. These folks are based out of DeepMind, and they're responsible for the model that was able to beat a human at Go. They have their model is a combination of 3 technologies. So it's deep learning concepts, Monte Carlo tree search, and then also they're running it on massive clusters of TPU pods. And they were not able to actually implement all of this model in Python. They had to revert to C++ in order to do it effectively. And we were able to port the model to Swift and saw precisely the same performance as the C++ instantiation, but only a fraction of the lines of code. And it was actually a much more efficient implementation in terms of like the way that it was configured. We've also been working with a team called OpenSpiel. They do reinforcement learning as well at DeepMind, and they've just recently open sourced the framework. If you would like to play with it, feel free to send pull requests or to use it in your academic work or at your work, and let us know how you like the Swift implementations. We've also focused on developer tooling, so we have all of our documentation available online. It's sort of auto-generated from the Swift. We also have sort of collab examples and notebooks available for you to use. And we also have support directly within VS Code, so not just Xcode, right? You're able to get those things that I mentioned before, semantic-aware autocomplete, jump to definition. And it's actually quite nice if you have experience using Python, which doesn't necessarily have those same benefits. So future direction, AD, in the process of being upstreamed. We're working on integration with mobile and embedded devices. You can see some of that work talked about in our open design meetings, which happen every Friday morning at 9 a.m. Pacific time. We're doing C++ interop, concurrency, and ownership. And if you'd like to get started, everything is on GitHub. It's all open source. We have a whole bunch of collabs available for you to try if you're new to machine learning or if you're a seasoned developer. And you can stay informed by joining our Google group, swift@tensorflow.org, by going to tensorflow.org/swift, and by checking out our GitHub repo. So thank you for coming today. Really excited to tell you a little bit more, and I think we have time for questions. So if you have any, feel free to ask. I'm delighted to answer about Swift or about TensorFlow in general or machine learning or what have you. So thank you.
Hi. I've heard of Swift, but I was curious, what's the GC story on Swift?
The GC?
Garbage collection?
Garbage collection, yes. So Swift is not garbage collected. That was one of the reasons why we decided to pursue that as opposed to something like Kotlin, which is. Garbage collected languages are not particularly well suited for many machine learning tasks, especially deep learning tasks. So that was one of the reasons why we selected Swift. Yep.
Excellent presentation, thank you. I'm actually not familiar with the concept of differential programming. Mm-hmm. And can you, I know it's sort of a general question, but can you drill down into what it is and why it's so important?
Right. So that's a great question. And differentiable programming is so kind of married to the idea of machine learning and deep learning because it's all about change over time and understanding sort of the gradients of the operations that you're performing, right? So machine learning and deep learning in particular is just a whole bunch of matmls and gradient computations. And if those are the only operations that you're performing, so just matrix operations over and over and over and over again, if you're able to take those very base Lego brick blocks and incorporate them directly into the language, directly into sort of the compiler behavior, it ends up giving you a lot of performance wins, and it also dramatically reduces the complexity that you as a human compiler have to have as you're architecting out your programs. So differentiable programming is so important to deep learning, I guess, because it's one of the most sort of foundational Lego bricks of deep learning as a concept, and understanding change over time.
What actually happens when you put that at differentiable annotation on?
Right. So with TensorFlow, if you have experience using that particular framework, the same concept happens when you apply something called gradient tape. And in TensorFlow, you would have like with gradient tape, and then you would start sort of collecting variables as you go through some sort of change operation. So you would just be sort of collecting variables in an array and understanding the differences between them. And that gets very difficult to wrap a person's brain around, or at least my brain. It's difficult to understand sort of how to deal efficiently with those variables, especially across clusters of machines, or if you have lots of variables or higher order differentiation operating simultaneously. So at differentiable does that, but without you having to define a gradient tape and having to keep track of all the variables yourself. It just does it for you.
So, is the future for Swift is to actually build all these mathematical libraries natively or to depend on Python? For instance, NumPy. Today, if you actually want to write some deep learning or machine learning algorithms in Swift, basically depend on NumPy. So,
Right.
1 year down the line or 2 years down the line, is the roadmap for Swift is to actually build all this natively?
That's a great question. So the roadmap for Swift itself, some of those libraries have already been built out. So this summer we had 4 Google Summer of Code students, 2 of which built out a library called SwiftML, which is essentially a scikit-learn replacement. 1 of which built out SwiftPlot, which is replacing Matplotlib. And then we're in the process of building out something called Penguin, which is a replacement for pandas but implemented in pure Swift. So the data science ecosystem and tooling in Swift is small, but it is growing. And you can use the Python implementations if you prefer, but if you want to see the performance benefits of operating in a language like Swift and not have to do the single threading, then you could just use the Swift implementations. Yes, all of that's in GitHub. Yep.
I think we got time for one more.
Hey, my question is, if you or anyone in your team has executed some standard training for some standard machine learning problems and compared performance for compared performance with Python or C++?
So I'm not sure I heard the question correctly.
Do you have specific numbers how TensorFlow for TF with Swift is how much better than TF with Python for some standard algorithms?
Right. So I guess the question, if I'm understanding correctly, do you have a performance comparison of Swift versus Python for doing the same operations?
Yeah.
Yeah. So I don't think that we have any listed on GitHub, though that would be really interesting to see. A couple of ad hoc examples that I can give is we recently partnered with a team at Google. I can't say which one because just sort of they haven't talked about the work that they've done publicly yet. But we were able to take their Python model, which took so about a minute to train on kind of a constrained device setting, and we were able to get it down to sub 1 second. Which is kind of awesome, and this is partially due to like it was kind of a spline-based model, so it wasn't doing anything too awful complex, and it was very sort of CPU focused as opposed to like massive cluster of GPUs. But we were able to see performance enhancements of over 100x, which is kind of crazy. Another example would be Jeremy Howard in one of the lectures that I referenced. He was able to implement a hyper-performant data pipeline using C instead of using sort of the typical Python tooling that you would see. And he got a 10x performance improvement there. So those are just a couple of examples. The performance benefits aren't due to TensorFlow being slow or unarchitect. Like it's not because of that. It's due to if you're using a typed language or if you're using C++, like you end up getting these sort of massive wins without having to try too awful hard. And whereas Python, like I love Python. Like it was one of my first language was BASIC because like text adventures on Apple IIs, but like my second language was Python. And even though it has a beautiful, vibrant ecosystem of products, it does have kind of very tangible performance limitations. Thank you.